Yeah, I'm just starting the recording. Let me check if everything is working. Yeah. Oh, it goes back. Okay, so I mean, I'm getting a feedback. Is there any? Oh, I think I need to mute this. Okay, there is no feedback now. Okay, so can you see my screen? Lecture 7.
Yes, sir. Yes, sir.
Yes, sir.
Okay. Yeah. So last week we talked about random variable. Okay, so yeah, we introduced what is called a random variable corresponding to a random experiment, and we said, okay, random variable can be any function from the sample space to R depending on the context, whatever you want, or whatever way you want to define it. Okay, so and we gave, I think we discussed 2 examples. Okay, so we denoted random variable as capital X. So usually we'll write capital X, capital Y, capital Z as random variables. So if there is a random experiment, so there is a sample space. If it is known to you, then you can define always a mapping. So basically, the purpose, okay, the purpose of introducing this variable is to associate. Okay, so the goal or the purpose is to associate numbers. Okay, as a numbers or to assign numbers to the sample points. Okay, so sample points could be anything. For example, we discussed about like throwing a pair of dice, and we said, okay, the outcomes could be a pair of numbers. But anyway, you can define a random variable depending on what you are interested in. For example, okay, so we talked about like this. So it is like 1, 2, 3, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. So x-axis is like one die. So let's say it is die 1, and it is die 2. And then these are the possible outcomes, which is a pair of numbers, x, y. X is the outcome of die 1, and y is the outcome of die 2. And x, capital X, the random variable, can be defined as the sum of the outcomes. Okay, so that is also an association, okay, for the ordered pair of numbers like outcomes of the die 1 and die 2. So the pair of dice to are real numbers. But really it depends on the context. So if we look at, if I'm interested to look at the, let's say, the sum of the outcomes, then I could define. If I are interested to look at the product, you interested to something else, you can define it something else. So we said, okay, it can be any function, but okay, there are quote unquote any function. Okay, so we will not go into depth of that, which functions are random variables, but we said, okay, a random variable, so it is a function sample space to the R such that, so this is the picture we had, I think, discussed, like if this is your sample space S, okay, and this is, let's say, the real number. So this is 0, this is positive, these are all negative real numbers. Then for every point here, okay, in the sample space, we can associate, let's say, a number. Okay, we can associate a number to all these outcomes, and such that whatever number you take from this real line, this is R, the real line, you pick any X, doesn't matter. Okay, any number you pick X, then the inverse of X must be an event. So that has to be the property of the function, and this is the function. Okay, so those functions are, let's say, the random variables, but really we are interested in to now to associate events as subsets of R. And why is that? Because we know calculus, okay? And sample space can be the sample points can be as abstract as possible depending on the context. As I told you one day, an example of, let's say, all tweets, okay? If you want to analyze some social media, data of social media like a social network like Facebook or Twitter, so all tweets could be sample points, like any tweet is a sample point. So this is not really, I mean, a difficult job to do actually. I mean, if you want to analyze all tweets, so but let's say we want to assign some value to it, okay? Then it would be easier to do that. And since we know calculus, so we can apply our basic theorems, fundamental theorems of calculus in order to get some insights, okay, about the data points, okay? So this is the purpose. So random variable is the purpose to associate numbers with the sample points, and next goal must be associating associate or explaining events, okay, as subsets of R through this mapping. Subsets of R, I mean subsets of the set of all real numbers through this random variable, through X. This is the goal, okay? And then we'll try to find out or calculate the probability of some of the events, okay? And yeah, so this is what we discussed. And then we said, okay, once we have a random variable, then this is an important quantity, which is x equal to small x, okay? So this is defined. So this is always an event. So whenever we consider probability of something, we mean that probability of an event, because probability is a function again from set of all events to 0, 1 or to non-negative numbers, okay? So this has to be an event then. Whenever we write like P of something in brackets, okay, so it has to be event. And what is this event? How and what is the meaning of this notation? We explained it's like probability of this event. So it is like all sample points from S such that the value of S is equal to X. So obviously then you can see here that this function X need not be 1, 1. Okay, need not be 1, 1 means multiple sample points can go to same real number, can be assigned the same real number. Like for example, some of the outcomes of the pair of dice could be same, like 5. Okay, 5 means could be 1 plus 3 or 3 plus 1. Okay, or 1 plus 4, 4 plus 1. So multiple sample points can take the same value. So yeah, so that means this is a set of sample points, so which is an event because it is a subset of the sample space. So yeah, and then we said that this is very important function. So this now can be treated as a function because it is defined for any small x. So it is a function, and we denoted it like f of x, and we called it, this is the PMF, because we are talking about discrete sample space. So for discrete sample space, we call it a probability mass function. So this is called PMF, the probability mass function of the random variable x. So once it is a function, then the question is, can any function be a PMF corresponding to some random variable? We said no, and we said we discussed two properties that it has to be, and property is very simple. We said that there has to be, I mean, this function has to satisfy two properties, and the first property was it has to be a non-negative function, so fx has to be bigger or equal to 0, and another was sum of fx, which is very natural. Sum of fx would be equal to 1. So all this x belongs to this x. This x we can define as a set of sample points, or we can say just a subset of all numbers which are defined for all the sample points. So it is like this set, you can consider it is the range set. Okay, you can consider this as the range set, a range set of x. So I mean, yeah. So this is how it is defined, because this x is a real number. Okay, you can consider this, or you can consider any real number, doesn't matter, because unless, so it could be a null event, I mean, so the null set. Okay, so we discussed about it. Okay, so these are the two important properties. If a function, we said it is a real valued function in general, and if it satisfies these two properties, we said okay, this is probability mass function of something. Now the question is, if I know this, now the question is, what is the advent? And not only that, we also found out this PMF of two random variables corresponding to two different random experiments, which we considered in last week. One was this rolling of a pair of dice, and another one, I think, was tossing a coin 4 times. Okay, so these were the examples we considered. Yeah. Yeah, so this was the example. We'll consider this example a little bit today also. So yeah, so this is the example consider. This is rolling or tossing a coin 4 times. Another one was just, yeah, so this is the pair of dice. Okay. Yeah, we talked about this. And why this function is important? Because this function will be used to calculate probability of other events, okay, of event of interest, let's say. Before we do that, so mm, there is something called probability histogram, or some just like histogram, okay, associated with a random variable. So what is that? So let's say we call it probability histogram. It is nothing but, okay, I'll come to that. Histogram. So it is a two-dimensional picture like this. X, let's say this is this. So it is like depending on the range set of X. For example, so if I consider, so let's say here, let me set my experiment. So let's say here it is this rolling of, or let's say tossing of a coin. Let's say the coin is unbiased. Okay, it's a balanced coin 4 times. So here we can say it is unbiased. So unbiased means all outcomes are equally likely. It's the head and tail. Okay, probability of getting head in a toss of the coin is half, and getting tail is also half. So 4 times. Okay, and then we defined X to be equal to the number of heads. Number of heads. This is how we had defined. Okay, so if this is the case, let's say, if this is the case, then what we'll write here, okay, is like the number of head could be 0. These are all the range of capital X, you can say like that. Head could be 1, head could be 2, head could be 3, and number of heads could be 4. And for all this, so this is the value X equal to 0, this is X equal to 1, this is X equal to 2, X equal to 3, X equal to 4. Now for all this X, values of X, we calculated what is the value of probability of X equal to X. That means we have found out what is this most small fx, okay? And these values will be here. We had written it down. You can go back and see the table, okay? Here. So if X equal to 0, then if X equal to 0, then fx equal to 1 by 16. X equal to 1, it is 4 by 16. X equal to 2, it is 6 by 16, and so on. Okay. And I think for 3 also it will be 4 by 16, and for 4 it will be 1 by 16. So yeah, so this is the probability mass function fx. This equals to fx. This is the probability mass function of this random variable. Now we want to plot this function. Okay, so just if you want to plot this, then I have this value x equal to 0, 1, 2, 3, and for x I have a value, let's say 1. Let's say here I have let's say here I have 1 by 16, and then somewhere here I have 4 by 16, and somewhere here let's say I have 6 by 16. These are the values only. Okay, so for 0 I'll have one value here, which is 1 by 16. For 1 it is actually 4 by 16. For 2 I think it is 6 by 16. And for 3, it is again 4 by 16. And for 4, it is 1 by 16. But whenever we will draw this picture, a histogram, we'll call it histogram, we'll not draw only just a line. We'll take a region here, which is, let's say, we'll draw it like this, from here to here. So whenever we are drawing a histogram, okay, then what we'll do is we'll represent this 0, this outcome, by the interval minus 0.5 to 0.5. Okay, so I had drawn the picture a little wrong. So the 0, since this is 0 here, so the y-axis would be here. Okay, y-axis would be here, let's say. Should be here. So then it is from minus 0.5 to 0.5. And then for 1, we'll have this from, this is, let's say, minus 0.5 to 0.5. Then here we'll take 0.5 to 1.5 and so on. So we'll take a length of 1 around the possible values of x. And then we'll have this, and then we'll go like this, and then this, and then this, and so on. Yeah. Then this is called the histogram. So in histogram, what we're trying to say here, that what are the possible values of small xc, okay, or the capital X, doesn't matter, when you have a non-zero probability. Then what we'll do is we spread a little bit. We just directly do not draw these lines that all these values, let's say these are the lines. So I just take this value. Corresponding to 0, it is 1 by 6. Corresponding to 1, it is 4 by 6, and so on. But we'll consider a spread around this values x, and the spread has length 1. So it is an interval of length 1. Okay. So basically what we're doing is we are drawing some kind of rectangle. Okay. Some kind of rectangle. And this meaning of this rectangle will be clear when we'll define what is something called a continuous random variable. So it is basically essentially what it means is around x. So if I want to approximate this random variable as a continuous random variable, that means here all these values are there, let's say. Okay. So then we'll see that this can be how much spreaded over this, over the entire x-axis. So that can be considered. In fact, this whole thing, the area of this rectangle, you see, is exactly the probability. So area of this, because the base, the area of the base, let's say if fx, if I take f equal to 0, let's say f of 0, that means small x equal to 0. It's nothing but the area of the rectangle. And let's say this rectangle is A, this is B, this is C, this is D, this is E. Now say it's area of the rectangle, and so on. So f of 4 is, let's say area of rectangle E. Okay. So it will give us an idea about continuous random variable. That means if these values on the x-axis would have been spread out over the entire region from 0 to 4, okay, a little extra from 4 and little, okay, extra from 0, like it is from minus 0.5 to, let's say, 4.5, then this is how it would look like. And this is like just the rectangle, thus area is exactly the probability, okay, of this. So this is the meaning, and this is how it is defined. Okay, whenever we will write a histogram corresponding to a random variable, it always means that this is how we should draw it. So yeah, so this is how we'll draw it. So this is called a histogram. This is one way to look at how fx, okay, is spreaded, okay, over x. This is one way to see that how the probabilities, okay, corresponding to each of these sample points, okay, is spreaded over the x-axis. And there is another diagram corresponding to this probability mass function, which is called a bar chart. Okay, so this is one thing. Another thing is called a bar chart. Somebody wants to ask something? Say something? No. Okay. So this is one way to look at the function, the probability mass function. Another way is like it is called a bar chart. And the bar chart, this you can also draw. It's like rectangle, but here we are not setting that the area is like the probability. So it is like anything where, so if it is 0, 1, 2, 3, 4, corresponding to the previous example, you can select this is 0, whatever the values are. It is like 1 by 16, and then this is 4 by 16, and I think it was 6 by 16. Okay, 6 by 16. Okay, so this is exactly not the y-axis, but these are the values. So then you can say, okay, this is a bar chart. Okay, this is a bar chart, something like that. So here we are not restricting the interval to be interval, I mean this x-axis, this interval which is spread around x. It's not of length 1. Okay, so this is a bar chart. This is called a bar chart. Sometimes this also gives us some idea about how, so it is a very small example, but if you, for example, you have thousands of possible outcomes, if you now plot a histogram, okay, and then squeeze the picture, then you will see like it is a continuous kind of a curve. Okay, and then there are some sample points where the probability is high, some points are probability low. From there, you get a complete picture about the probability of each individual outcome. So you have an idea about the probabilities of happening of some of these sample points. Okay, so this is just a convenient. Okay, for your convenience you can draw it to make some insights about how it is behaving. Okay, as an entire function. Okay, if so for example, okay, why it is required, so you can just have a vector of all these values. Vector of values means just the points here. Okay, this will define a vector, all these effects like we defined last day. So it is just this is also called a probability vector. When you have a discrete random variable, you can have this vector, all this vector, but it may not give you an insight. Okay, but if you can picturize this way, if you just draw the histogram or the bar chart, okay, then it will give you an impression. Okay, it will give you an impression about the random variable and the corresponding probabilities of the corresponding sample points. Not exact sample points, but range of the random variable. Yeah. So these two things are important to see, to visualize the probability mass function of a random variable. And then another crucial function. This is one function corresponding to a random variable. And there is another important function corresponding to a random variable, which is called as the distribution function or the cumulative distribution. Okay. So cumulative distribution. So what happens? Distribution of a random variable. Let's say x. Okay. So what happens? I said, okay, PMF gives an idea about probability
Sir,
at each sample point. Yes.
sir, we can also show the continuous sample space by the random variable, right?
Yeah, we'll talk about that little later. We'll talk about continuous random variable today. Okay.
Okay, sir.
Yeah. So here, whatever we are discussing, it is everything is discrete. Okay. And so I'll come back to that example, which I think one day I discussed about throwing a pin on the wall. Okay. I'll come back to that. Okay. So my question was actually originally, what is the probability of hitting the wall at a particular point? Okay. So, and I said, okay, we have to consider this problem in a different way because this domain is continuous. So what is the probability at each point? Okay, so it cannot be treated as a discrete random variable. So there is a problem. Okay, yeah. So we'll talk about that. Okay? So before that, okay, we talked about this event x equal to small x. Okay, now we'll talk about, sometimes it is important to know this one as well. Okay, this is also an event which you defined earlier. So this event is like set of all sample points such that the value of x at S is less equal to x. Okay. So that means, let's say my question is the probability of an event, which is like this. So let's say in our previous example, I want to say what is the probability that the number of heads is, let's say, less equal to 3, okay, or at most 3. So that could be a possible event, okay. So this function also depends on this real number x, and I can directly say and this function is actually called the cumulative distribution function, and this is nothing but, as I mean, you can see that this is nothing but sum of what, all the x, because we are dealing with discrete random variables. So how can you say it? It is like sum of all, you can say sum ft, and t is less equal to x, where this is our PMF. Okay, so this is how it is defined. Okay, so this is called the cumulative distribution function, and this function is denoted as capital Fx. So sometimes we'll be interested to know what kind of function is this. Okay, so this function has a meaning. I mean, if you see here, if you just see the histogram, so these, all these peaks, okay, they are like the fx. But if you say capital X is less equal to small x, then basically it is, if you pick any x, then the left of that peak, okay, what is the area? That is what the question is. Okay, so this has also a meaning. So this is also very important, and this is called cumulative. Why cumulative? Because we are adding up. Okay, we are adding up, so we are taking sum of all the values of the sum of all the probabilities. Okay, so for example, I mean, just let us calculate the PMF, or the cumulative, or sometimes it is called CDF. Okay, cumulative distribution function, CDF. Okay, it is not, instead of PMF, it is called CDF. So cumulative distribution function. It is very simple. The idea is very simple. Okay, so for example, if you look at the previous example, what we had, f of 0 was 1 by 16, f of 1, this is the number of heads, okay, uh, is 4 by 16, f of 2 is like 6 by 16, and f of 3, which is 4 by 16, okay, and f of 4 is also there. F 4 is also 1 by 16, I guess, right? F of 4 was what? Yeah. So now, what is then f0? F0 remains f0, which is 1 by 16. What is f of 1? So this is f0 plus f of 1, which is 5 by 16. Then what is f of 2, which will be f of 0 plus f of 1 plus f of 2, so which is 11 by 16. And then we have f of 3, which will be f of 0 plus f of 1 plus f of 2 plus f of 3, which will be 15 by 16. And f of 4, which is sum of all these, which will be 1, because of the property of the probability mass function, okay, which you already discussed last day. So we can say then that fx, how it is defined now. So it's, if it is a function from R to R, okay, so this function, you see, this small x can be anything, okay, so this f is again a function from R to R. You can say it is non-negative, but anyway, so you can say R to R also, okay. So yeah, so this is how it is defined. Now if I want to explicitly write this function, for example, in this particular case, so this is 0 when x is less than 0, 1 by 16 when 0 less equal to x less than 1, and 5 by 16, okay, where 1 is less equal to x and less than 2, okay. Then we'll have it 11 by 16 when 2 less than equal to x less than 3, and then 15 by 16, 15 by 16, which is 3 less equal to x less than 4, and then 1, of course, when x is, let's say, bigger equal to 4. So this is a nice function. Actually, you can see the property. See, this is monotonically increasing these values. When you increase x, this of course will increase, because every time you are adding here some extra terms, okay, from the previous, we are adding some extra term. Of course, this is monotonically increasing function. So So the question is now, if I give you any function, okay, when can it be a CDF of something, like CDF of some random variable? So what are the properties it should have? Okay, that you can explore and you can see like what are the properties you can have, and this is a very nice function. Okay, so okay, maybe I can just write it down. So when I mean what are the properties of this kind of a function, which is a CDF, the cumulative distribution function? Okay, so okay, let me first say, I mean, let me first ask you, what is your guess? Okay, so let's say properties of CDF, cumulative distribution function. So it is like, okay, so first of all, let's say what is f of infinity? Now, what is the meaning of f of infinity? Infinity is not a number, of course, because we define f of x. Okay, so meaning, let's say we can say the limit x goes to infinity, let's say, okay, and fx. So if I define it this way, okay, if I denote it this way, what is that? What is the value?
Infinity.
1.
One.
Infinity, sir. Because it's
Mm.
adding something infinite times.
So
Hmm.
one.
One.
So
1.
1.
Okay, so the answer is one. Question is why? Okay, so I don't want to answer this. Okay, you have to think about it. Okay, second property, f of minus infinity, what should it be? Same way, like limit x goes to minus infinity fx. What should be its value?
0.
0.
0. Okay, so question is why, and it is the correct answer. Question is why. I mean, think about the picture. Picture is what the area. Okay, this area. Okay, if you consider the area of this rectangle up to x. So here, so let us any x here. Let's say x here up to x. So this is the area, okay, of the curve. Let's say if we consider this as a curve, okay, so area of this curve up to x. Okay, so this is what it is. So if x equal to infinity, then you just sum up all this. Okay, and minus infinity means, of course, there is of course no area, but okay, so this is the case. Okay, and of course, if you take any number a less than b, of course, if a will be less equal to fb, is always a model increasing function because of its definition. So question is why. I mean, these are the simple properties of this function. Okay, for any, if a is less than b, it is always monotonically increasing function.
So
So
I had a
yeah,
doubt. So
yeah,
always
please.
CDF is defined as x less than equal to x. Like I can't
Yes,
define
yes.
CDF in any other way I like.
What is your question?
So I can't define CDF in any other way I like. Like that's how the function is defined always.
Yes, yes, yes. So this is the probability. So fx, the meaning of this is the probability of capital X less equal to small x. Yeah, this is the event. Probability of if this event is the cumulative distribution function. Why it is cumulative? Because we already defined what is probability of x equal to x, small x. Now, if I from the left hand side, if I go up to certain extent x, okay, small x, then what is the area under this? Something like that. Okay, the concept of area is coming because of this picture. This is like a continuous spreading of this. Okay, but it will be much more clear when we talk about continuous random variable next. Okay, but you can just say addition of all the probabilities still x. Okay, yeah, somebody saying something. Yeah, please go ahead.
Sir, we can also take greater than, sir. Suppose the
Yeah,
t is greater
also,
than x.
yeah, get at the next you can say, but that will be 1 minus of this. I mean, you
Yeah.
say probability of x is greater than x, so this will be what? Probability of 1 minus. So probability of x equal to bigger than x means what? All those events small x such that sx is bigger than x, but this is less equal to. So it will be 1 minus fx. So it is 1 minus x less equal to x, right? So yeah. Okay, so now, so the thing is, why these are important? Okay, small f, capital F, and so on. Okay, if you so there are two things. One is, I mean, this is from, I mean, this is for the students who are interested to do data analysis and something like that. There are two things. Okay, You always have to. Okay, so what is happening is, see, I mean, I cannot discuss every possible directions, okay, or applications of this kind of concepts, okay, due to the time limit, okay. So we have to maintain a schedule, okay. But sometimes I will just mention 2 or 3 things, and you may think about it, okay, or read more about it, and to know like what is happening, okay. Okay, so what I said here is corresponding to capital X, I am defining 2 functions, which is fx and capital Fx. Now there are 2 things. One is this could be given to you already, okay? And then from these 2 functions, what is your goal would be? Your goal would be to calculate probability of certain events, okay? But what happens in real life, and this is what we'll do in this course actually, okay? So either small fx or capital Fx will be given to you, and from that you will be asked to find the probability of certain events. But in real life, you have to guess, okay, what is this, from the data. So in real life, this is not given to you, okay? So if you want to calculate probability of happening of something, okay, for example, I mean, let me give you an example, a silly example maybe. Suppose today some of you are friends to each other, okay? Now if I ask you, what is the probability that after 5 years you'll remain friends to each other? And this is a serious question, okay? So you can, how do you model, how do you come up with an answer? So that means whenever I ask you something which is physical in a sense, which is real, which comes from real life, okay, then you have to model, you have to do something, okay. So you have to do something so that it can be explained in a mathematical language. So it has to be explained, let's say, in a probabilistic model. I can give you an example of that model. What I ask, let's say, so all of you are like certain points here, okay, certain points. And now if we're friends with each other, let's say today, starting from today, then there will be some links like this, okay. So friendship means, let's say, there is a link between these vertices, let's say, okay, or the nodes, and each node represent one of you, okay. Now, so this is a graph structure. Now this is a graph. Now what is a graph? Graph is a set of nodes and some links between the nodes, or some edges between the nodes. Now this graph structure is a structure of time. It depends. T is today. Now T is evolving. So this graph structure is evolving because tomorrow you may become friends of some other people from this class, from this set of students who have registered in this course, let's say. So then there will be certain new links tomorrow. So if T varies starting from 0, then this structure means some links will get broken, okay. So due to something, due to some kind of a thing, okay. So this links, some of these links will break, okay. So this is an evolving network. Now my question is, let's say after T equal to 500 days or 600 days, I'm asking now, let's say I consider this as a node and this as a node. My question is, at T equal to 500, what is the possibility that there is a link? So that means existence of a link comes with a probability. Okay, then you have to find out what is the probability that this link will exist after T equal to 500 or at T equal to 500 or T bigger equal to 500. Okay, so this is a simple question, but it is hard to answer. Okay, any real life problem, it is very simple to explain the problem. Okay, but when you are solving that problem, it takes a little time to understand how to fit it into a mathematical model, and then you have to answer this. Then the question will be, for example, what is my random variable here? That will be the first question. If this is the random variable, how do I define this small x? How do I estimate this small fx or capital Fx? If one of this is known, can I solve, okay, that particular question? That what is the probability that this link still exists? Okay, so this is kind of a real situation where you have to answer this. Okay, so real life problems are always difficult. They are not very simple because you have to estimate this. These are not given. Okay, somehow you need to make some observations about your data, and then you have to find. So you have to fit into the model, and then you have to ask the right question, and then you have to come up with the right answer. Okay. Okay, so once we know this fx and capital Fx, okay, then question is what more can we say about the random variable, and that we will discuss a little later. Before that, let us develop the concept of continuous random variable. Okay. Okay. So now we'll talk about what is called a continuous random variable. So as I discussed, I think before, I think in the second lecture, so continuous meaning the sample space is not countable. Okay. So whenever we discuss continuous random variable, that means the sample space. The sample space is not countable. Not countable includes that it is not countably infinite. Okay, not countable. And what are the examples of not countable sets? They are like intervals, enter real line, which is continuous. Okay, it is not discrete. For example, as I said, that rational numbers, okay, are also a rational set of rational numbers is a countable in a set because it is discrete. Okay, you cannot say this entire part of the line consists of all rational numbers, sum of the rational numbers, all rational numbers, or any point between this number to this number, okay, are rational. We cannot say this. You always have to say like there are some points here. It is discrete. Okay, it is not continuous. But we, as we said before, like we always assume, okay, it cannot be proved, it cannot be disproved that the real line is continuous. Okay, so any point on this line corresponds to a number, or any number corresponds to a point on this line. Okay, so this line is infinite extended. In fact, if you just pick an interval, let's say closed interval, open interval, or let's say one side open, another side closed, all these are all examples of uncountable sets. Okay, so here that means my sample space is like that. Okay, now what we'll do is the way we have developed concepts of the probability mass function distribution, or some examples we consider. Okay, similar way we'll also develop the concepts of probability, not exactly mass function, but we call it a distribution function. Like for the discrete random variable, we also said, okay, mass has a meaning in terms of physics. Okay, all these probabilities can be considered as masses. Okay, I think you should know it, so I didn't discuss about why it is called a mass function, but there is a mass interpretation, a mass interpretation of all these probabilities. Okay, how much? So for example, in fact, in a histogram also you can say how much mass is there. Something you're putting here, let's say this area, something you're putting on this particular line. Okay, oh, this is not the histogram here, something is putting on this line. Okay, so how much is that? So this is the mass function. That's why it's called the mass function. The inspiration is from physics. As I said before, most of the concepts in probability theory, okay, was originated from the ideas of physics. It's like experiment itself is a physical experiment. So once you generate data from some physical experiment, you need to analyze the data. Okay, and that's how you need to know these concepts. Anyway, so the thing is, so here, for the case of continuous random variable, okay, our sample space could be like a line or like something which is continuous. Okay, if it is a two-dimensional space, which is not a part of this course here right now, okay, and part of this discussion right now, but it could be like this. Okay, here it could be like a rectangle, which is, let's say, part of x-axis, y-axis. Like I said, like it is a part of the wall. Okay, and you are throwing some pain. Okay, what is the probability of hitting that this pain will hit at a particular point? What is the question? Okay. Okay, so sample space are like that. So if you want me to give you an example, I'll pick an example like this. Suppose there is a freeway. So because I want to bring an analogy, so like it's like straight road. Okay, starting from, let's say, from here to here, it's, let's say, it is some number of some kilometers. So it's, let's say, 200 or 100 kilometers. Okay, 100-kilometer road. Okay, this is continuous. This road is continuous. Okay, now you are interested to know, let's say, okay, that what is the probability, what is the possibility, let's say, okay, that there will be an accident at any given location. Let's say there will be an accident here, there will be an accident here, something like that. So since our domain is not discrete, domain is continuous, instead of asking that question that at a particular point, okay, we'll always ask the question at an interval. So the right question here is, what is the probability that there will be an accident from this region, from this particular region? So the entire region, 0 to this 100 kilometer, let's say it is from some road from Calcutta to so let's say Mumbai, okay, this national highway, okay. So what is, or maybe up to Benares, so what is, whatever it is. So a particular full road, like full length road, let's say, okay. So it's not a particular point. That is not, that is a wrong question to ask whenever we have a continuous domain, okay. In fact, you can also ask like from, I mean, you can pick particulars, let's say, interval of this entire road, and then say you can have that this is like k kilometers or d kilometers, okay. And then what is the probability that there will be an accident, okay, in this region which has length d. In fact, you can also ask like, what is the probability that there will be an accident, okay, of any interval, on any interval of length d. These are the right questions to ask, okay, for the case of mm, continuous random variable, okay. And continuous random variable, okay. So then the first question is, how do I bring out a concept of let's say mass function, okay. So as I said, will not ask this question. You'll see little later why this is not a right question to ask, okay, at a particular point here, at a particular point. But we always have to consider an interval, okay. So let's say if you're analyzing the height, okay, or the weight or the height, let's say, for all the students from, let's say, the height from 4 to 6 feet, okay. Then the right question would be, what is the probability that there are students, okay, there will be a student whose height is from 6 to 6.5, okay. So this is the right question to ask, okay. And why is that, I'll tell you. But before that, instead of probability mass function here, we'll call probability density function, okay. So density is important here. So now probability. Oh, by the way, I think I forgot to mention this. I mean, I just remember this. There is an exam, I think, next Tuesday, okay? Next Tuesday means not tomorrow Tuesday, okay? The next week Tuesday. I think next year Tuesday, but every detail will be, I think, will be communicated to you about the exam. Okay, so probability density function. Probability density function. This is what we'll define. And the idea will be, I mean, if I just draw this histogram, I mean, this is a nice picture actually, the histogram, it gives you a good idea. So it is something like, suppose it is something like that, okay? So something like that. I mean, this is, let's say, the histogram, something like that, okay? Then you can assume like this is a continuous domain. So in this case, these are the points. In continuous, this is the entire domain, let's say. This is the entire domain. And then it is something like this, something like this. This curve is something like that. So it is a curve like this, okay? So on the entire, some probabilities are defined for any interval, a sub-interval of this, let's say A to B. And so the corresponding curve looks like this, okay? It's not just a sum of some rectangles, but it is a curve like this, okay? For the case of continuous random variable. And whenever I define density function, I define it for a particular interval like this interval, okay? So here I'll define probability density function, okay, which will denote it as small fx. The same notation is same. This is also small x fx. That was also small fx, but that was corresponding to discrete random variable. Here it is continuous random variable. This is called probability density function, or sometimes called PDF, okay, probability density function, which will define it as not probability of x equal to x, but probability of a less equal to x less equal to b for any a and b. A, b could be any real number, or a is less than b. Okay, a, b are any two real numbers. And this is defined as this. The event is A to B. Okay, I'll come to that. So it is fx equal to dx. So what I mean here is this step is not here. Okay, so any function fx is said to be a density function if probability of a less equal to x less equal to b is equal to this a to b fx dx. So this is wrong. I mean, our goal is to find out this probability. Okay, goal. Let me write it this way. So the goal here is to calculate or define probability for events and of this kind of this trips type, like a less than equal to x less equal to b, and x is the random variable here. So given a and b, so this is like probability of all such x belongs to S such that a less than equal to x of S and less than equal to b. So then I'll say a function fx is said to be a density function. Okay, so here f is a function from R to R. Okay, this is said to be a density function. Yes.
Sir, you said that fx is a density function, but sir, for a random variable, for a particular point, what is the meaning of density at that point?
I'll come to that. Okay. So whenever I say a function f R to R is a probability density function corresponding to a random variable, okay, it represents the probability density function corresponding to a random variable. That means whenever I take a less than equal to x less than equal to b this event, then probability of this has to be given by this area under this curve. So okay, here I also wrote a and b. So let's say this is not a and b, but this is, let's say, a and b. So, and let's say this is equal to f of x. So the area, okay, area here, this is the area. Okay, so can you guys hear me?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes.
Okay. So fx, a real valued function, let's say any function like this, it will be called the probability density function, which explains probability density function corresponding to the continuous random variable capital X if probability of happening of this event, that a less than equal to x less than equal to b, x is lying between here to here, is the area under this f. Then I'll call this f, this function f, okay, this function f as the PDF of the probability density function of the random variable x. So this is the definition. Now here you see, if I pick a particular number, x equal to some c, then what happens? Probability, then it has to be, this can be explained as a less than equal to x less than equal to c less than equal to c. Okay, I can always say this. So that means probability of x equal to c for any c is nothing but 0. Now let me go back to my example of throwing a pen on the wall. If we pick up any particular point f, then the probability of hitting that is always equal to 0 because it is a continuous domain. So whenever we want to then calculate a positive probability, so then we always have to talk about an area. So we have to discretize this domain, okay, and then we have to talk about the area. So there is an entire area, which is, let's say, A, and then we'll not call this particular point, but we'll say the probability that it will hit this particular area. So for a continuous domain, asking this question, probability at a particular point, x equal to x or x equal to some c, It's a wrong question because it is always equal to 0. Okay, you
So,
always have to ask for probability of an interval.
so,
Yeah, yeah, please go
so
ahead.
should it be tending to zero and not exactly zero?
According to the definition, it is always 0. A to A fx dx is what? That is what I said last day also. You can say it is tending to 0, but actually if you see, that's why if you read the basic mathematics, we always say area of a point is 0. Okay, area of a point is 0. Okay, so whenever we are hitting this, we say that it will hit at this point, we'll say that this is a wrong question to ask. The right question is, I have to fix an area, like small area around this, and then we ask the question, what is the probability that it will hit on that particular area? Okay, so this is the right question to ask.
Sir,
Yeah, please go ahead. Yeah.
sir, I think it it should be we can write it to be exactly zero for a particular point, because
Yeah.
if we define the probability to be equal to the limit, so then we first
Mm-hmm.
evaluate the limit and then we assign the probability. And if the limit evaluates to zero, the
Mm-hmm.
probability of a very small area, as the area goes to zero, what's the
Mm-hmm.
probability of uh, choosing that area, and then that limit evaluates to zero, and then we assign it to the probability function, output of the probability function p of x is equal to c. And so then I think we can say that it's exactly zero. So is that the correct way to think about it?
Yeah. So the thing is, the area of a point is 0. This is actually the answer. So if you got it. I mean, what I said, area of the point is, see, suppose you say it is not equal to 0, then this definition. That's why I always say, whenever you are studying mathematics, you always have to consider some framework, some kind of assumption, some kind of this is, yeah. So some kind of a setup. Okay. So for the case of continuous random variable, we always assume that point area of a point is equal to 0. So the right question will be, you pick a point and pick an area around that, and then you ask, and this area is non-zero if and only if it is not a point. If you take a point, the area is
Yes,
always
sir.
0.
Understood.
Okay.
Yes, sir. Got
Yeah.
it. Got it.
Yeah. So because of this property, now, now here what I have. Okay. So because of this property, okay, what do we have
Excuse
now?
me, sir.
Yes.
Sir, is it wrong if someone says like in the same case if you just give someone this like event that you have to throw a pen at this point, and if we do it infinite times and like one of the infinite times it happens that the pen actually get in the same point, so can you say like now the probability is not zero, although it's tending to zero but not zero?
Yeah. So the thing is, whenever you say there is an area, so there is a positive probability. That means it has an area. Whenever you say some event, okay, let's in this particular example I'm talking about. Okay, so in this particular example, whenever you say the hitting of this, that means there is a concept of area, but point has no area. So in that sense, I mean, you can say large number of times if I throw this, that will hit this particular point, but we'll say it will never hit that particular point. So that somebody was, I think Walker was saying, talking about quantum mechanics. Okay, so the thing is, what is a point? Can you find a point on the wall? It is very difficult to find a point on the wall, because you can always put a microscope, okay, on the wall, and you see that if you if you increase the power of your lens, okay, then you will get a breakthrough region. You can visualize a point inside a point, right? I mean, you just enlarge and the region, okay,
Yes, sir.
just by
Yeah.
putting a microscope. So you never reach to a point actually. Okay, so whenever I say that this is a point, it actually has some area, okay, but a point you cannot actually see, okay, something like that. So in that sense, it makes sense that probability of that is equal to at a point, hitting at a point equal to 0, because you never get a point actually. So if I ask you find all the points, and if you points on a particular region of the wall, then you will see that whenever you put a dot using a pen or pencil, whatever you use, a dot, you can only plot finitely many points, or maybe countably infinite. You can never reach to uncountably infinite because of the same philosophy which I said in lecture 2, second lecture, that you never find out a point next to another point. You can never find it out because it does not exist. Like a number, real number, because here it is a pair of real number, right? Even I said any real number, if I give you, you cannot find the next real number, immediate next real number. That means it does not exist. Because if you say it exists, I will ask you to find it. So you actually cannot find all the points because it does not exist. Because it does not exist in a sense that you cannot find it. So if you cannot find it, so what do I say? I can only explain mathematically saying that, okay, it does not exist, because if it exists, we could have already found it out. This is our limitation, you could also say, okay, that is our limitation, that we cannot have a device which can find all the points. Okay, so on the real line, you cannot find, I mean, if you pick any real number, okay, you cannot find the next immediate real number because it does not exist. So you cannot find all the points. So this question is actually a little bit vague, I would say, because you cannot find all the points. Okay, so since I do not know all the points, so this question is baseless. If I ask, what is the probability that it will hit a particular point? So it is safe to say, according to the model, according to the definition, that probability is 0. Okay, now because of this property, so it implies, which is very different from, now next observation is very different from discrete case. This implies that probability of A less than equal to X less than equal to B, this is same as probability of A less than equal to X less than B. By the way, in our case, we do not have this situation, okay? This is just an abstract example. We always have the range as the real line, okay? This one, okay, real line. Okay, so that's why I'm writing A less than equal to B, okay?
Sir,
Yes.
sir,
Yeah.
the diagram you just drawn, sir, can you show that?
Yeah.
Sir, in
Yeah.
that, can we say that that this probability? No, sir, the grade one. The in which we have written A. So I can I say that the probability of choosing a particular area is is actually what is the probability that I choose that area over all the areas, over all the similar areas, like one grid over all the.
Yeah. You can do that. Yeah. So this is how we define what is called this accident.
And
When
in
I
that
said,
way,
we said,
and in that way, I can explain that if I choose an infinite amount of rather infinite points, so the area would get smaller and smaller, and I'll have less and less
yeah,
probability of area.
yes. Yeah, you're right. So yeah, so the next thing is, you can say like this is less than X less equal to B, and this is exactly equal to probability of A less than X less than B. So any point does not matter. A point does not actually matter. In fact, this thing you must have observed also in math 1 or maybe in 10 plus 2, that when you calculate area under a curve, okay, so that is done by integration, right? A to B fx dx. When you calculate, then you always assume that fx is a function from ab to r. This is a mathematical convenience, okay, and then you say that what is the value of this and this. But area under this, and if you say this, there is no big difference actually to take AB to R, because at a particular point, the area does not matter. Okay, so you write the same thing. So this is what is happening here actually. If you go through the meaning of this definition, like it is an integration of fx dx, okay? So whether it is A is included or not included, this particular point, it actually doesn't matter much when you calculate the probability. So it doesn't matter much when you calculate the probability here. Yeah, when you calculate the areas, so when you calculate the probability. Now the question is, here you see, earlier I had a very concrete definition of small fx, that fx equal to probability of capital X equal to small x. But here we don't have this. Here we are defining the density function in a reverse way. We are saying, okay, so earlier we had probability of capital X equal to small x, which is equal to f of x, the probability mass function. But here we are saying, given a function f of x, which is a real valued function, given a function like this, okay, then we are saying that it is a density function corresponding to the random variable x if it can explain the probability of this event. Meaning, if the area under this curve from A to B gives me the probability of this happening of this event, okay, then only I call this f as the probability density function. So there is not a very ready-made way of finding fx given the random variable. Okay. So the question is now, first of all, that what are the properties of a probability density function?
Sir, I
Okay.
had a doubt.
Yes.
So, like you said, it doesn't matter whether it is a closed interval or an open interval, right? Like, what if my probability function is, say, discontinuous at A and B? Like, would it still be the same?
Yeah, that is a good question. Yeah, it will still be the same, like you do. I mean, sorry. So, like you do. I mean, so if I ask you this question, I think, I mean, this is not discussed in Math 1 uh, due to the assumption that everybody knows this. But this is a crucial question. I mean, this is a nice question. So, if I ask you this question, because this is very related to math, very much related to Math 1, when can you calculate this? If fx is a discontinuous function, can you calculate the area? What is your answer? So we always assume that fx is continuous. Okay, that fs is something fx, and then you calculate. This is a nice function. Let's say I draw. Okay, it can be very complicated. So a to b, and then this is the area. Now instead of this function, suppose I say this is my function. Forget about the endpoints. Let's say this is discontinuous at this particular point c. Okay, so this is the this is the function. Okay, so this is a curve, and this is a curve, not a line. So this function is discontinuous at c. I mean, this there is a gap here. Okay, this point is not exactly this one. One of this is not there. So what is the area? Is it this same? Is it the same or not? I mean, treating this discontinuous function as a continuous function. Okay, because in treating it means, I mean, we are drawing like this. Okay, like, I mean, drawing like this. Okay, this, but it is not. It is not a continuous function. So the question is, can I consider this area under this entire thing as the area under this function, although the function is discontinuous? Can I say this? And this is a very basic fundamental question. The question is now, under what condition of this function f I can calculate this, the continuity of this function f, small fx, this function, the integrand. Okay, is it necessary? And the answer is, you'll be surprised to know, maybe if you don't know, that is not necessary. In fact, even if a function f is discontinuous at countably infinitely many points, or maybe countable points, so that means it could be either countable, so it is discontinuous at finite number of points, or countably infinitely many points, still the area will be same. Still the area will be same. So this integration you can calculate. This is actually what you have done. I mean, explaining the area, rectangle, all these things. Okay, sum of these areas and this and that. So this is what is called a Riemann integration. Okay, Riemann integration. And Riemann integration says, Riemann said that, okay, any function which is discontinuous, even if at countable points, okay, this still can be calculated, still exist. So it does not matter only at 2 points. It need not be continuous. Okay, this fx at infinitely many points, still the area will be same, because it does not matter much. And why? So you have to
Sir,
just a minute. You have to actually keep this in mind. I'm always saying it is countable infinite. Whenever I say countable infinite, okay, that means it is at discrete points. There is no interval where the function is discontinuous. It is not there. There is no interval such that, just a minute, my pen sometimes stops working. Okay, so it is not like at this entire interval the function is not continuous. It is not like that. I'm not saying the area of this is same as the area of this entire thing. I'm not saying that. I'm saying only at infinitely many points. That means it is a discrete point. The function is discontinuous at discrete points, not discontinuous at the stretch of a continuous domain or like an interval. It's not, because then it will be uncountable. Okay, so this function is integrable fx, even if it is discontinuous at countable infinitely many points. So that's why it does not matter much whether it is discontinuous at two n points. Even if it is discontinuous at infinitely many points, does not matter. The area will still be same. Yeah, please go ahead.
sir,
Yeah, please.
sir, if a function is discontinuous as countable point, so sir, can we simply say that we can break the interval in that form and calculate the integration?
Yeah. So that's why at that particular point, what is the value? It does not match. So yeah, you can say that. Yeah. So let's say I draw a function which is like this, and then again this, and again this. Okay. So at this particular point, let's say the function is discontinuous. At this particular point, function is discontinuous. At this particular point, does not match. The area, okay, of this area of the area under this curve, okay, is same. If you consider this as a thorough, like let's say here it is A to B, the entire region, okay, A to B, whatever it is, and oh, this is the integration. Okay, just doesn't matter. So it will be the same value, A to B, entire function, whatever way it is detained. So then you can define, like let's say it is A to A1, it is A2, then it is A3, and this is A4, which is AB. So it is A to A1. That's how you can write this dx plus again A1 to A2, okay, A1 to A2, and then A2 to A3, then A3 to A4. This is always equality. Yeah, what you said is correct. So it does not matter much. Okay. Now the question is, can any function like fx, can any function, there's a question now, can any function f from, let's say, R to R, okay, can any function act or serve as a PDF for some continuous random variable? The answer is no, as usual. For some continuous random variable, the answer is no. And then there are two conditions. Okay, the condition one is, so fx has to satisfy two conditions. And like the similar analogy, like whatever we had in discrete, same thing we'll have for the case of continuous random variable. One is if x has to be a non-negative function, meaning the values are non-negative, and here the area under the entire curve should be equal to 1. Earlier we had sum of this, here the sum is replaced by the area. Okay, now like last day, now we'll consider an example of a function and we'll find out whether this is a candidate for a PDF or not. So let's say my fx is equal to this, k e to the power minus 3x, where x is bigger than 0 and 0 elsewhere. So this is a non-negative function, right? Or maybe we can say this is the function. Find the values of k, because k is a constant. Find the values of k for which fx represent represent a PDF of a random variable x, and then let's say find probability of this, let's say 0.5 less equal to x less equal to 1. See here in this, now see, gradually, this is the main observation here, gradually we are going away from the concept of sample space. When we introduce continuous random variable, even we did not bother to say what is a sample space. We only said a function fx, any real valued function, when can it be a PDF for some random variable? We forgot about the sample space itself. Okay, and next thing is, I did not discuss here, let's say, that given the random variable, how do you define fx? How do you define its PDF? I actually introduced the PDF as a reverse concept. A function is given to me. Can I say that it is a random variable? It's a PDF of some random variable. I said, yes, it can be if the probability of the random variable, let's say, probability of the event correspond to a random variable like a less than equal to x is equal to the area. That means if this function satisfies some properties, then it is representing a PDF for some random variable, and we'll calculate the probability of the events corresponding to that random variable. So we don't even care what is the sample space. So in a realistic situation, when you have data, okay, so if it is continuous time data, like you are measuring temperature for a, let's say, or maybe something you are measuring which is on a continuous time. Let's say the graph, I give you an example. This is time is continuous, it is evolving. Okay, if whenever I say t equal to 500 after 500 days, so it's an entire interval, okay, 0 to 500 days. So whenever something is continuous, okay, then the question is, I mean, the random variable is a continuous random variable. Then the question is not how to find fx. The question is from the definition of the random variable. The question is what kind of fx can represent this random variable? That is the question now. So given a data, we have to estimate this function if it is a continuous random variable. Given this, I mean, given some particular data, I have to estimate this function and which can explain my event. Okay. So then that is the question. So for example, okay, let us solve this problem. So now, in order to show that this represent this function fx represent a PDF for some random variable, what I have to show whether this function is satisfying those two properties which I defined earlier. Okay, this function is it non-negative? Like, is it this bigger or equal to 0 for all x or any k?
Yes. Yes, sir.
Okay.
Yes, sir.
Okay.
If
Sir,
positive.
Yeah. So then
sir,
we need. Yeah. Somebody has any question? Yeah.
yes,
Go
sir.
ahead. Go ahead.
Sir, is there any possibility that one continuous random variable has many PDF functions to represent that?
See, the question here is we ask the reverse question. Okay. Given a function, whether it can represent a random variable or not. That is our question. I mean, fx defines the random variable x. Here we are not bothered about, for the case of discrete random variable, we started with x and we defined what is the PMF, probability of x equal to x. And then we also ask a reverse question. But here we are only focusing on the reverse question, that fx, now whether it can explain some random variable or not. Even if it can explain, that means if it satisfies those properties, then it will definitely explain some random variable. Then we calculate the probability of events corresponding to that random variable. Now your question is the reverse. Given a random variable, whether it can have two CDF or not, I would say no. In fact, I would say, I'll go further and say, this question is not important at all because we are not defining fx from x. We are defining fx to x. Why not? Because what will happen if it is the case, let's say, that there are two functions, let's say fx and gx. Both are PDF, corresponding to some x particular random variable. They are corresponding to some x random variable. Then probability of a less than equal to x for any a and b, this is equal to minus infinity to infinity fx dx, and this is also equal to sorry, not minus infinity but a to b, a to b gx dx, and this is true for any ab. So what does it mean? What can we say from here to here?
Yes, sir. It can more than. Okay, sir. Understood.
Okay. So now the thing is, here fx is bigger or equal to 0. Now we need to check whether this value is 1 or not. Okay, if it is 1 for some values of k, then I'll say for those values of k, this will represent a PDF. Okay, for some random variable. So that means I need to check what is this? This is minus infinity to infinity fx dx, which is equal to minus infinity to infinity. Okay, I may do a lot of mistakes, okay, when I'm calculating this. I'm not good at calculation at all. iPad storage full. Not now. Okay, K. What am I writing? I was correct. Okay, minus infinity to infinity. This was K e to the power minus 3x dx, but when x is positive, okay, so I think, yeah, so that means for other values it is 0. So this is 0 to, I think, this. So then which is, what is this? K will come out. So this is 0 to infinity e to the power 3x dx, which is what? So this will be K limit, let's say some, what should I write? T goes to infinity. Okay, 0 to t e to the minus 3x dx, which is equal to what? So K limit some t to infinity. This will be e to the power minus 3x by minus 3. That is from 0 to t, which is equal to what? So this is K. It is 3. So yeah, so t goes to infinity then. So it will go to 0 and minus 0. So it will minus here. So it is 3. K by 3. Now this has to be equal to 1. So that means for only one value of K, it is a PDF. Now since, yeah, because of this. So this implies, it implies K equal to 3. So for K equal to 3, it is this, that it is a PDF corresponding to some random variable. Now I want to find out this. Very easy. I have, so now I want to calculate this P 0.5 less than equal to X less than equal to 1, or whatever less than 1, doesn't matter. Less equal to 1. So now I see, I don't care where does it come from. My definition is this is from 0.5 to 1. And K is here 3 e to the power minus 3x dx. That's it. This is my probability. So I don't even know what is this X explicitly. I said it is corresponding to some random variable, and whose probability, even the probability of that, this event corresponding to that random variable, now can be calculated using this. So this is 0.5, I think. So whatever it is, so yeah, you can calculate that. So this is the thing. Okay. Now, so this is, so I mean, this is similar to PMF because of the same thing, that it is explaining probability of an event, but instead of a point, it is it is an interval, because in a continuous random variable, since it is a continuous space, so we'll always ask the question of interval. It's not a particular point. So it is any interval. There it was any point. Here it is any interval. And here this probability is calculated using this formula, mm, integration. And there it was just a particular point. Okay, here it is a to b fx dx. Now the question is, okay, so now the question is, can we have a similar concept like cumulative distribution function there. So can we have a cumulative density function? Okay, here. So our cumulative distribution function. Yes, we have the same concept. So here I will write cumulative relative density function, density or distribution function of a random variable which is continuous. Okay, of a continuous random variable. And it is the same thing because here now we have a perfect same meaning of this, because here this is a continuous domain because it is from minus infinity to 2x. So here we are not changing anything because this is a meaning, this is a continuous domain. This is an interval. This interval is, so this is, let's say r. So if it is x, so this is minus infinity to x. This is the interval. Okay, minus infinity. So and this can be calculated as from minus infinity to 2x some f, oh not fx, but let's say ft. Okay, and x could be any number. So x is from infinity to minus infinity. So this is called cumulative density function. Now, what are the properties? You can again check that properties of this function. Okay, you can check that this is minus infinity means it is 0, if infinity is 1, and if a same properties, if a is less equal to if b, if a less than equal to or less than b. Okay, but now if we just recall what is called first fundamental theorem of integral calculus, okay, integration. If we just recall, we can have a ready-made definition of this. Okay, so question is, what is the big deal? Question is if we know fx, okay, fx, what can we say? What can we say about other events, about probability of certain events? Probability of certain events. Okay, so it is just the fundamental theorem calculus, because probability of a less than equal to x less than equal to b, this will be equal to fb minus fa. Now can anybody tell me why this is correct? This one was equal to a to b fx dx, and this is equal to fb is equal to what? Fx equal to c. Now how do I define? Minus infinity to x. Okay, so
Yes.
fb,
Minus infinity to
yeah,
b.
yeah, minus infinity to b fx dx minus minus infinity to a fx dx. Now my question is, why these are equal?
Sir, by area we can prove, sir.
Yeah, so this is what is the fundamental theorem of calculus. You can prove that. Okay, not only that, see here again, there is an interesting fact from here. There is again an interesting fact from here. If you use the concept of antiderivative or antiderivative, what can you say? So fx, capital F, the cumulative distribution function, is defined in terms of the PDF. Now my question is, can the PDF be defined in terms of cumulative PDF?
Sir, it's the slope.
So if this is the integration, then this will be, small f will be the derivative of capital F, if the derivative exists, of course. So here, so this is our first observation. This is our observation 1, and the second observation 2. Okay, that fx is equal to ddx of fx whenever, see, this is a very big question. When does this derivative exist? This is a big question. We'll not go to the, we'll not analyze that question, but let us just say the derivative exists. Most of the cases the derivative exists. We'll assume like that way. Derivative exist. Okay, so here it is the mapping from capital F to small f, and earlier we had defined capital F from a small f. Okay, so these two are important concepts. Okay, so for example, in this case, in this earlier example, this one, if I ask now, what is the cumulative density function here for this fx? Okay, then what do we have to do? We have to just integrate it. Okay, can you do that? And I will not do it. So what is the question here? Question here is this represent CDF, this represent PDF for k equal to 3. So if this is a PDF, then what is the corresponding CDF, the cumulative distribution function? What do we have to do? So from the small f, if I ask you to find out the capital F, it will be just the integration from minus infinity to x ft dt, and whatever this is, that will be the. Okay, let us do it. Let me do it. So calculate me the question. Let me set up the question. The question is calculate the CDF cumulative density function of the PDF defined above. That is what was that? Fx was k equal to 3 e to the power minus 3x when x is bigger than 0. I think and 0 otherwise. Okay, then if you want to find it, then what happens? So if you want to do it, then fx equal to, so answer is what? Fx is equal to minus infinity to x ft dt, which is 0 to x, because it is when x is positive, then only it is non-zero, otherwise it is 0. So this is 3 e to the power minus 3t dt, which will be what? Minus e to the power minus 3t 0 to x. 3 will get cancelled, so this will be 1 minus e to the power minus 3x. Okay, so therefore, what is our function? Fx. This we can now define 0 when x is less equal to 0. 1 minus 3x when x is bigger than 0. Now see, if I want to find out the same probability of that event, okay, yeah, this event, using the capital F, then also you can do. So here we use directly the formula, but here we have a ready-made formula. Probability of A less equal, this is a ready-made formula. Probability of this equal to Fp minus Fa, if F is known. So we can directly use the formula and we can say probability of 0.5 less equal to x, capital X less equal to 1 is f of 1 minus f of 0.5. Whatever it is, you can just find it out. Okay, so yeah, so this is a little bit about continuous random variable. So the basic idea is we had a random experiment, which means we have a sample space, a set of events, basically the probability space. So the set of events and so on. Okay. From here, we build up the concept of random variable. Okay, and then we talked about that the random variable can be of two types. One is discrete, one is continuous. Here maximum thing is defined by sum or by series. Here it is by integration. Integration is the tool here, and there sum is the tool. Okay. Now once we have a random variable, then we said, okay, we can have PMF or PDF. Okay, and we have cumulative probability distribution or distribution function. So let me write it like. So we have CDF, okay, cumulative distribution function or cumulative density function, whatever it is, for discrete and continuous respectively. And then what we said is this fx equal to probability of x equal to x. So x is playing a big role. Here we said at a to b, fx dx equal to probability of a less equal to x less equal to b. So the fundamental difference between this discrete and continuous random variable is that this is pointwise. So that's what is mass function, mass at a point. So this is pointwise and this is interval. Okay, this is a fundamental difference. Okay. So here we started with example of random variable and we came up to the definition of PMF. But here we directly said that if we have a function fx which has certain properties, then that must correspond to some random variable, and then the probability of this event defined by that random variable is given by this integration. Okay, so there is a big jump here. And whenever we have introduced this concept, there is no mention of sample space because we don't care. Okay, we only care about random variable. Random variable will correspond to some sample, so whatever it is. Okay, doesn't matter. So random variable means what now? So the question of random variable comes very important now. Random variable means it is a function, real world function across sample points. It means it is measuring something. It is giving you a number corresponding to some random experiment. You perform certain experiment, even if you do not know sample points. You perform certain kind of experiments. If you measure something, you always get a value. And those values are this x. And then everything makes sense. Okay. Now the thing is, we'll now try to find out some more things about random variables. Okay. Some more things about random variable means exploiting or using these functions like PMF, PDF, CDF. What can we say about the properties or different properties of the random variable, capital X? This is what we'll try to find out now. Because if we can say anything about the random variable and it is related or the events are related to that random variable, so always there is a connection about finding probability of the events corresponding to the random variable. So our next goal is, so this is our next goal. Next goal is, okay, determine properties of random variable corresponding to or exploiting or using corresponding to these functions. Okay, this is our next goal, and the reminder here is how to think of a random variable. Think of random variable as a measured value, random variable value of the random variable. So as measuring, let's say, measuring something. Okay, so random variable takes that particular value. That means you are measuring something, okay, corresponding to the random experiment. You're measuring something and it gives a value, and that is your random variable. The random variable corresponds to a function. Random variable is a function from the sample space to R. Real numbers. So these real numbers are giving you a value corresponding to the experiment. Now you want to discover, you want to determine the properties of these values, which will actually give you the properties of the corresponding events or the properties of the corresponding experiment. Yeah, so we'll stop here today and we'll talk about it tomorrow. If you have any questions, you can ask me now. So after the lecture, I'll upload the video in the YouTube, and I'm also I am also trying to make the subtitle correct because yeah, in some places in the subtitle, you'll see that whatever I'm saying, it is not printing that. So because my accent is different from whatever the algorithm is there in YouTube. I mean the algorithm for generation of the subtitle. So it cannot recognize, I can recognize whatever I'm saying. Okay. So I'll try to fix that, but it will take a lot of time. So if you watch the subtitles, okay, so you can see that there is a difference, whatever I'm saying and whatever they're displaying. But anyway, you can understand it. Okay, that is not a problem. I mean, if you don't, then you can let me know.
So,
Yeah,
so I had a doubt. So, in the
please.
example of heating a